Welcome back to Mechanics and Control of Robotic Manipulator. Last few classes, what we have seen differential kinematics, statics, and we have started talking about robot dynamics in general. So where we were talk about why robot dynamics and what are the, you can say, subclassification and how we can obtain in that two popular method we have seen. But this particular lecture, what you call lecture 14, we would be talking more about what you so called like generalized equations. So we would be writing matrix and vector format. So this is what we are going to call equations of motion, that we are going to write into different you can say perspective. In the sense, we would be writing the equations of motion in the joint space, or you call configuration space. The other one, we would be writing this into a, you call inertial, or sometimes people call operational or task space. So we are thinking about the operational space is the second part, and the configuration space is the first part. So in that sense, we will actually like go forward. So we would be actually like seeing the same disclaimer all the time, and we would be actually like trying to address equations of motion in configuration space. Then we would be seeing the operational space aspect. So let us actually like go slide by slide, then we can see what exactly it does. So this is what the general model in a simple form, where actually tau you can write in terms of function of q dot and q double dot. In the sense, these are actually like motion variable, and these are actually like cause of motion, right? So these are actually like we have seen. But what we are actually like going little more here, so we are actually like trying to write this into a, you can say, simplified way, because we are all the time we are looking about this, so that I can actually like double integrate and I can actually like get the q of t, right? So this is what we are actually like seeing. So for that, what we have to do, we have to actually like first integrate this with respect to time. Then you can actually like see that that would give the q dot. Then again integrate q dot with respect to time, then you will get the q of t. So this is what our interest. Then what we can see, this equation we can write in a other form. What we can see, so we can write f equal to ma plus something, right? So that is what we are actually like writing. So where a is acceleration and m is inertia and f is input, and this is a remaining vector. Okay, so if you recall what we have done in the you can say simple mass spring damper system, so we written actually like this, right? So this is the linear equation where mass spring damper all there. So right now this equation I'm writing as actually like mx double dot equal to f minus b x dot minus kx. So then I can write x double dot is actually like m inverse, in the sense 1 by m. So f minus b x dot minus, or you can say I write it, make it common. So this I can write. So this is what we are interested. So for that, what I'm writing, this is I'm rewriting in this form. So where you can see that there is one component called you can say inertia matrix, because this is vector and these are actually like vectors. So this is the inertia matrix which would be giving, you can say, multiplication of acceleration. This is equivalent to what you call your Newton second law, F equal to ma kind of thing, and these are other effects, and this is what your input. So now even this also can be further actually like modified. Some of the people have done this, so little detail. So we can actually like see that, so usually this q dot would be function of, you can say, if I assume that this is a vertical you can say parallel manipulator, vertical serial manipulator, the two like planar, you can see this gravity is actually like pulling, right? So then you can see that the gravity I can make it separate, then my controller is easy. I can make a gravity compensated control, right? So in the sense, what I am trying to do, I am rewriting this equation same, but this n of q comma q dot, I am making it a gravity separate, and you can say remaining term I am putting it here. So this is one detailed model. Even some more detailed model, what we can see, this is consist of, you can say, centripetal and Coriolis terms, and even the friction terms later on we can come. But right now we assume that it's simple rigid body, where the centripetal and you call Coriolis term we can bring it. So this is written and this is also written. This can be further divided into, one is actually like centripetal term, so which is actually like is something like half, you can say, omega squared r. So not half, you can say omega squared r, that we are equating. In the sense, here it is actually like joint velocities. So q transpose something into q trans, like q dot transpose into something into q dot. So this something I am calling as actually like centripetal matrix. And now you can see that when you will get the Coriolis is actually like linear velocity combined with you call angular velocity, so that you can write as, since it is all actually like q dot, so you can see that q dot as, you can say, vector. So now you can see that if I actually like make it this way, So this will give what so called, you can say, Coriolis term. So this is what we are actually like trying to see. So then you can see this is what the general model. So we have done already one example where the two are serial manipulator tau 1 and tau 2 we obtained. So now we are actually like trying to, you can say, make it this way. So I am writing tau 1, tau 2 separate, and then M matrix, and so theta 1 double dot, theta 2 double dot separate, and then I am trying to write remaining as n of theta vector and theta dot vector. Okay, so the theta dot vector is actually like theta 1 dot, theta 2 dot, theta vector is theta 1 and theta 2. So like this is what I am actually like interested. Now if you see, so where are the theta double dots are coming? So this is one theta double dot, in the sense this is a, I call M11, and this is actually like M12, and in this term you can see this is M21, and this term is M22. So in the sense M11, M12, M21 and M22 is the matrix which is going to call hereafter as a inertia matrix. Now if I do this, this is what the remaining term, so I can make it as a vector. So if I multiply this matrix and vector, that would give these terms, right? So now you can see further, you can see that the q dot squared, okay, q dot 2, or it's like q2 dot squared and q1 dot squared is coming in 1 and 2, that I can separate it. So this is, I can call actually like something else, and this is actually like you can see theta 1 dot, theta 2 dot. This is actually like equivalent to what you also call a Coriolis component. And further what you can see here, this is multiply with the g, which is the gravity, or you can say gravity pull, that multiply with the sum term. This is, I can bring it as g1 and g2, and this I multiply with the g, this is what the g vector. So like that I'm actually like able to make. So now this is what the inertia matrix, and you can see that this is what the centripetal effect, right? So now if I actually like multiply, you can see that this is multiply with this, right, theta 1 dot. So in the sense this will come actually like minus m2 l1 l2 s2, you can say theta 2 dot, right? So now if I multiply this, what happened, theta 1 dot, theta 2 dot will come, right? So now if I multiply this, what it will come? So this is actually like theta 1 dot squared, and that would be theta 1 dot squared, right? So in the sense you can see that that is actually like going to come. So in the sense you can see that this is actually like theta 1 dot, theta 2 dot also come, and theta 2 dot squared also come. That is what we are actually like written here. So you can see this is what your case, and here you can see theta 1 dot squared, and here in this case you can see theta 1 dot, theta 2 dot and theta 2 dot squared. So but the common term you can see here m2 l1 l2, but here 2, but here actually like not there, right? So that is what we are actually like trying to get. So in the sense you can see that actually like going to come, right? So now this is the same way you can actually like expand. So the Coriolis effect, I can actually like make it separate. So you can see this is what the Coriolis effect, right? So now further what you can actually like do, if you do the gravity effect, then that is a g1 g2, then you can see this is what the gravity terms. So now what we have done, so we have done actually like something what we were discussed earlier, so that we have done. So what this, so this form we have written, right? So now I am actually like interested to see the operational space category. So what that means, so I know some relation between operational to configuration space. What is that? So that is nothing but the, you can say, Jacobian information. Even we can see that mu is, I can write as a function of q, but this is not really concerned. If I take the time derivative, this will give. Now this is what I am assuming, that the known relation between these two. So now what I can do, I can actually like further differentiate what that will give. So mu double dot is actually like j of q into q double dot plus j dot of q into q dot, right? So now what we know already, q double dot as in the form of m inverse of, you can see like the earlier case whatever you have seen, that you can all actually like put it in the sense tau minus n of q comma q dot in general. Okay, so now you can see that this q double dot you have got it, and q dot you can get it as, so j q inverse into mu dot, right? So if I substitute everything here, what I can do, I can see that this I can write in terms of completely in a single vector, and further from the statics what you know, the tau I can write as a j transpose of q into f. So what we know again, so this is what we know from here, right? And this is what we know from here. I'm actually like replacing those things here. So in the sense what I'm trying to do, this is relation I know, and I'm actually like putting that here, and similarly this information tau, so which is actually like there, that also I'm putting. Okay, so now what I'm trying to do, I'm trying to maintain everything in single space where these all inertial, or sorry, you can say operational space variable, right? So this is what I'm actually trying to do. Now I'm actually like making it, so what you can see, this whole multiply with the mu double dot, that is look like m mu into mu double dot, and this whole multiply with this, and this all together I can put as n of mu or small n of mu, that is equivalent to f. So this is what we are actually like saying, that everything in terms of one single space, this is nothing but operational space. So for that what we have done, we have taken the information which are available. So this information, in fact the information what available is this function of q with respect to this is the forward kinematic that we have differentiated. This differential kinematics have come, forward differential kinematics, that you integrated further, then you got the acceleration equation, and then you can rewrite that into q double dot, that you substitute here, and this f you can actually like get in terms of tau, or tau you can write in terms of f, that you substitute here. So in the sense tau I replace this equation, and the q double dot in terms of mu, that is what I've done here. So now I substitute everything here and rewrite in the initial term and the remaining term separate. So then what I got, this equation, this is what I'm going to call as, you can say, the equations of motion in the operational, or you so call task space. So now this is what individual matrix, what you call mu, you can say inertia matrix in task space, and this is the inertia, you can say other vector in the task space. Okay, so now with that you can see that you got one more clarity. So how the equations of motion in configuration space and motion in operational space can be obtained. Further in the next session or next lecture we would be talking about the properties of the individual matrix what we have obtained in the equations of motion. For example, if you talk about this inertia matrix is always like positive definite, in the sense it can be 0 or more than, you can say, 0. If it is 0, there is no, you can say, body exists, that is what the role, in the sense the inertia matrix supposed to be positive definite matrix. Further, this is actually like symmetric, in the sense you can see this, you can actually get it. So these are all the property we would be seeing in the next, you can say, lecture. So with that, I'm actually closing this particular session, and we will see, you can say, this live session on Tuesday, and meet, you can say, further. If you have any questions, we can meet in the middle of, you can say, the days as a short recap. With that, I'm actually closing this particular session. See you on Tuesday. Bye bye. Take care.